All right, good afternoon, everyone, and welcome to the May 2016 meeting of the SME Stamping and Dies Technical Group. And also, this would be the SME Metalforming Simulation quarterly web meeting. We are having a great pleasure today where we are welcoming a guest presenter from Triboform. Who is a virtual tribology simulation software provider. And they are going to share with us some information regarding how they can enhance and improve the already existing technology used for metal forming simulations by giving better and more reliable feedback for how to treat lubrication and friction of the complex system that is the interaction between sheet metal and dies. We are joined today also, Brianne was on camera a little bit earlier. I think what I'm going to end up doing is I'm going to end up suppressing a few of these webcams so that we can just not be so distracted by the everyone's faces in the screen, and we can give our full attention to Dr. Hole, who is our guest speaker from Triboform. So I guess without further ado, I would like to give the floor over to Dr. Hole, who is joining us from Triboform to introduce this new dimension in sheet metal forming simulations and an introduction to Triboform software.
Okay, thank you very much for this kind introduction. My name is Paul. I am the CTO of Triboform Engineering. We developed a software solution for the simulation of sheet metal forming simulation. So Triboform Engineering is a company, a software engineering company. We are started in 2013 as a spin-off company of the University of Twente. We started with two persons, which is me. I did a PhD in Tribology, and a colleague of mine, and he did his PhD on sheet metal forming simulations. At this moment, we are with 7 employees, among others with 2 engineers, application engineers, and 2 software developers. Our software or our company has 3 main pillars. So we provide engineering services and projects regarding tribology-related issues that our customers have in production. We develop a software solution, Triboform, and this presentation will mainly focus on the Triboform software. And for the Triboform software, we also require input. So it's kind of like material testing. For material modeling, you also need data, experimental data. Well, the same holds for the Tribology software that we provide. We also require some experimental testing, and we also provide these testing facilities to acquire the data that we need for our Triboform software. So the objective of this presentation, first of all, to shed light on the importance of friction in sheet metal forming processes, to discuss on the influence of sheet material, the lubrication and tooling material on friction, and which friction coefficient to be used in sheet metal forming simulations. And the ultimate goal of this presentation is to answer the question how to bring your forming simulation to the next level by including accurate friction and lubrication data. Well, during this presentation, I will first focus on why should we model friction, why friction modeling, how to model friction, and then enclosure. Well, if you look at why friction modeling, I would like to discuss the industrial trends and needs that we observe in industry, and tribology, friction, and lubrication in sheet metal forming. So what influences tribology and how important is tribology in sheet metal forming simulations? How to model friction, starting with our software, the Triboform software. We'll give a presentation about how it works, what input do you have to provide as a user to our software, following with 2 industrial application cases in which we will show the Triboform software and what you can do with the TriboForm software applied to real-scale industrial applications. And a closure, concluding with the benefits and new developments that we are currently working on at Triboform Engineering. So if we look at sheet metal forming in general, if we look at the developments that we see in metal forming simulation technology, then the past years we've seen a lot of developments on software codes, so software codes to predict the quality of sheet metal form parts. We've seen a lot of developments on material modeling, material type, material properties. The past years a lot of material models have been developed to describe very accurately the material behavior. Also on process and robustness, we see more and more developments going on in this field. But what we do not see is really a lot of developments in the field of friction and tribology. Still often a fixed value for the friction coefficient is used, the Coulomb friction coefficient. We know from practice and from experience that the friction coefficient is in fact not a constant, but it depends on different dependencies. And to our belief, making a better description of friction and tribology in stamping simulations will give you the potential to further optimize quality of parts, reduce time, and lower costs of new developments. Well, if we look at friction, the friction coefficient, we normally speak about a friction coefficient. We normally speak about a tribology system because it's in fact not one number, but it depends on a lot of dependencies. Amongst others, influence on friction has your sheet material. So what kind of material are you using? What are the properties of your sheet material? What is the coating, the surface finish? What is the surface roughness of your sheet material? Tooling, also important if you look at the tribology system. So what is the type of material that you are using? What is the surface finish? What is the surface roughness of your tooling material? Lubrication, type of lubricant. Do you have a liquid? Do you have a hot melt or a different kind of lubricant? And what is the amount of lubricant that you apply? And process conditions of your press. Do you have a hydraulic press? Do you have a mechanical press? What are the pressures used? What are the velocities used? The temperature will have an influence on tribology. And all these different dependencies, they intercorrelate with each other. So if you change one of these dependencies, you will also see that your tribology system will change and that you will have a different tribological behavior in your forming operation. What we see in industry is an increasing trend or an increasing variety of sheet and coating materials, tooling materials, lubricants, combinations, different lubricant combinations, process conditions and runs. And of course it increases the problem of friction and how to solve this issue, accounting for all these different dependencies. Well, if we look at the current state of the art of friction modeling, then nowadays still often a Coulomb friction coefficient is used, so a fixed value for the friction coefficient. We know that the fixed value is not a very accurate description for the tribology that we have in sheet metal forming simulations. A more advanced approach is to experimentally determine the friction coefficient. If we look at Europe, Germany, then an approach that is used quite often is to measure friction coefficients with friction testers. So we see, for example, the rotational friction tester of Tata Steel. We know Filzek in Germany with a strip-tall tester. Ratio in Germany also have a strip-tall tester. And all these testers can be perfectly used, let's say, to rank tribology systems. But at the same time, we know that if we have the same tribology system, so if we have the same metal lubricant combination, and we do the same experiments at these different test setups, then we also know that we'll get different values for the friction coefficient. And the question remains then, which value should you choose as an input for your finite element simulation? Another approach is to determine the friction coefficient by inverse modeling. For example, by using cylindrical cups. So based on experiments, the friction coefficient can be reverse engineered from the experimental results. What we believe in, however, is not to measure friction, but to really understand friction. And for that purpose, we develop the TriboForm software. So the TriboForm software can be used to calculate realistic frictional behavior, time and location dependent, and I will come back on that in the remaining of this presentation. Triboform physically describes friction and tribology under metal forming conditions. In the past years, we have done projects with the companies that you see here at the bottom of the sheet. So we do projects with the larger OEM automotive companies, but also with the steel suppliers, with aluminum suppliers, with lubricant suppliers, tooling suppliers, and we also do these projects with these customers to acquire all the information that we require as an input for the TriboForm software. So if we look at the TriboForm software itself, first of all, I'd like to note that there's a very nice introduction movie to our company at our website. I will not show it during this webinar because I don't think that the movie will run smoothly. But if you're interested, you can check our introduction movie at www.triboform.com. If we look at the software projects that we provide, then you see here a summary. So we provide our standalone software package, the TriboForm Analyzer. Using the TriboForm Analyzer, you can select a tribology system, and a tribology system depends on the sheet material that you are using, the lubricant, and the tooling that you are using. The selection that you make, a friction model, is then, let's say, called from a TriboForm library. The TriboForm library consists of different tribology systems, so different metal lubricant combinations. The TriboForm Analyzer or the TriboForm software is provided with a default TriboForm library, and this library includes different metal lubricant combinations, 150 in total. And using the TriboForm Analyzer, you can select a sheet metal combination, and you can export the selected tribology system to a finite element package such as Autoform to use this friction model in your Autoform simulation. Well, I will come back on these three products in this presentation, starting with the TriboForm Analyzer. So what you see here is let's say a snapshot of our TriboForm Analyzer. If we open the TriboForm Analyzer, you will see this screen. So we have a 3D viewport in the middle. This is the gray area. At the left side, you see the input that is required from the user. So we have a tab sheet, we have a tab lubricant, and we have a tab tooling. And I will go through these different tabs to present which information is required from the user, starting with the sheet material. So if you click on the sheet material, you will see a screen like this. And in this screen, we will give up, let's say, the setup of the sheet material. So which group of material do you have? Is it still uncoated? These are drop-down boxes, so you can select from these boxes. Is it still uncoated? Do you have a coated steel? Do you have an aluminum, for example? Well, and if you make a selection of your type of material, well, then you can make a selection of the type or the grade. So do you have a melt steel? Do you have a EG? Do you have a GI coating, for example? And you can select the supplier, so the supplier of the sheet material. After that, you can select some surface options. So what kind of surface finish do you have on your material? Do you, for example, have an EDT, so electrodischarge textured material, or do you have a different kind of surface finish? You can make that selection over here, and then you can give up a roughness value. As I mentioned, these are drop-down boxes, so if we look, for example, to the roughness SA value, you can select, well, I have a roughness value of 1, of 1.5, or 2.0. And once you've made your selection complete, then you can confirm, and then your selected sheet material will be plotted to the 3D viewport. So here you see a real three-dimensional surface texture of the sheet material that has been given up in the input section of the TriboForm Analyzer. If you would have selected a different sheet material, then you would also have a different surface topography shown in the viewport of the TriboForm Analyzer. This is a real three-dimensional meshed surface texture, and this surface texture is stored in the TriboForm Library. So if the selection of the sheet is complete, we have confirmed it, then we can go next. And in the next input tab, we're going to select the lubrication. So what type of lubricant do we have? Do we have a drawing oil? Do we have a hot melt? Or do we have a different other kind of lubricant? Supplier and type we can select, and we can select a amount of lubricant. And if we have selected an amount of lubricant, and we have confirmed our input of the lubricant, then you will see in your right side that a blue surface is plotted on top of the surface texture. So if I go one slide back and I go one slide forward, then you will see that a surface is representing the lubricant is now plotted in the 3D viewport as well. So in this case, you can see how much lubricant you should apply to fill, let's say, all the valleys of your surface texture. So it gives you a feeling how much your surface is filled with lubricant if you get for a specific lubrication amount. So the next step is to define the tooling. We can define a type. So do we have tool steel? Do we have, for example, G70L material, or do we have a other type of tool steel? We can again select a surface finish. It's now on default, but it can, for example, be manual polished or machine polished. And then you can give up a roughness value, so an SA value of the surface topography of the tooling. And if you have provided this information, you can again confirm, and then you will see that a third body describing the tooling surface is now plotted in the TriboForm Analyzer. So at this moment, the tribology system is known. So we have now selected the sheet material, we have selected the lubricant, we have selected the tooling. So now we can go on in the TriboForm Analyzer, and we can go to Analysis. If we go to Analysis, we will see 4 input text tabs describing the pressure, describing the strain, the velocity, and the temperature. And you see bounds, so it's a minimum value and a maximum value. And these are in fact the bounds for which the friction model has been generated. So we generate a friction model in advance, and this friction model is a 4-dimensional friction model as function of the contact pressure, the strain in the material, the velocity, and the temperature. We store this friction model in the TriboForm Library. You as a user, you select your tribology system, and then if you push evaluate, then we know which tribology system, which friction model to load from the TriboForm Library. So the tribology, the friction model is now loaded, and it also gives you the possibility to visualize results. For example, we can visualize the amount of surface deformation of a surface texture for a given normal load, for a given strain in the material, a temperature and velocity. So we have included two different lubrication amounts. We have included a normal lubrication. In this case, you see the lubricant, which is represented by the blue area, and you see that there are still some asperities of the surface which are coming out of the lubricant. And we see an increased lubrication amount, and in that case you see that the complete surface is filled with lubrication. In general, the left figure will result in a higher friction coefficient compared to the right figure. We can also animate this. So if I push this button, then we now see an animation in the TriboForm Analyzer, and you see the deformation of the surface texture. You also see the, let's say, the sliding tracks from the surface, from the tooling surface, which are penetrated into the sheet surface. And we can also view that for an increased lubrication amount. And then you will see that all the asperities are now below the lubrication amount. In this case, you will have lubrication effects, and which will result in a lower value for the friction coefficient. Okay, so that was in fact the animation. We can also have a look at the friction model in 2D or in 3D. In this sheet, you see the three-dimensional plot. So we have plotted here the friction coefficient as function of the pressure, so that is the nominal contact pressure, and the sliding velocity. And now you see that we have actually a three-dimensional friction model. We have our friction coefficient at the vertical axis, we have our pressure at the horizontal axis, and we have our velocity at the horizontal axis as well. In height, we see the straining of the material. So what we see here is that we have a pressure dependency, and if we increase the strain in the sheet material, at a certain moment you will also have a velocity dependency. So this is a four-dimensional friction model, and it's hard to interpret it from this figure. But the next step is to export this friction model to a finite element simulation package, to AutoForm, for example. And what you then will get is a file that you can read in your finite element simulation using AutoForm, and then this four-dimensional friction model is used directly in your AutoForm simulation. So a few words about the TriboForm library. We have seen now the TriboForm Analyzer. That is the, let's say, the GUI interface that you will see as a user. Using the TriboForm Analyzer, the TriboForm Library is called, in which different metal lubricant combinations are stored. And as we've seen also in the analyzer, is that in this TriboForm Library is a friction model stored as function of contact pressure, relative sliding velocity, the interface temperature, and the strain in the sheet material. And this allows you to direct simulate the sheet and tool roughness variation and lubrication amount. So it gives you the possibility to play around with the roughness of your sheet, with the roughness of your tooling, and with the lubrication amount, and to see what the influence is on your friction coefficient. And as I mentioned, the TriboForm Analyzer is provided with a default TriboForm library, which consists out of 150 friction cards, so 150 different sheet metal combinations. And we also provide the possibility to provide customized TriboForm libraries. So if you have a specific metal, sheet material, specific tooling, or a specific lubricant, then we can analyze this Tribology system. We can generate a TriboForm library for you. You can open this TriboForm library in the TriboForm Analyzer and export your results to AutoForm, for example. So if we look at this coupling between the TriboForm Analyzer and finite element simulation packages, such as AutoForm, Then using the TriboForm Analyzer, you have exported a friction card, and you can import this friction card in your finite element simulation. So this allows you to have a very efficient approach to calculate time and location dependent friction coefficients in metal forming simulations. So as an example, we have here a front fender. And this animation will show you the development of the friction coefficient. And at the moment contact occurs, so this is this moment, then you see that friction coefficients are calculated at locations where you have contact. So we will play it again. Friction coefficients that are shown are in between 0.13 and 0.18. And now you see that really a time and location dependent friction coefficient is calculated. And you also see that in high pressure regimes, so in die radii, for example, we will find lower friction coefficients. So high pressures, high strains in a material results in lower friction coefficients. And also underneath the blank holder, for example, we find lower contact pressures resulting in somewhat higher friction coefficients. So next to the friction coefficient, we also provide additional features. So because we are accounting for the real three-dimensional surface textures of topographies of the sheet material and the tooling, we can also account for direction dependency. So what is the influence of, for example, your rolling direction compared to the transverse direction on your friction coefficient? And we also provide the possibility to provide a friction card per tooling. So if your punch, for example, has a different roughness than your blank holder or your die, then we can assign different friction cards for the different tooling. So if we look at our licensing scheme, so the TriboForm software is can be acquired as an annual license, single user, node locked, or multiple users floating in a network. The TriboForm Analyzer can be licensed, as well as the TriboForm FEM Plug-In. So you can use, for example, the TriboForm Analyzer at 1 or 2 computers, and use the TriboForm FEM Plug-In so that you use these advanced friction models at multiple computers to your choice. Well, together with this license, we also provide, well, of course, the software sales, but also including updates and technical support, the generation of customer-specific friction cards. So if you have a specific metal lubricant combination which is not in the default library, then we can analyze this system for you and add it to your customized TriboForm library. And next to that, we also provide engineering projects and services next to the license. So next is to look at some applications and validation cases. For this purpose, I would like to discuss 2 different application cases. One of the door outer Mercedes C-Class and one of the door inner Volvo XC90. So starting with the door outer. So the question of Mercedes was, if we look at the door outer, is that they had problems in try-out production. So from try-out, they had fractures in the product. But at the same time, they know that if they go from try-out to the full-scale production run, that these problems will disappear. And what they want is to have a software tool to, let's say, bridge the gap between try-out production and to mass production. We have analyzed this door outer for Daimler. Some insights. So the tooling material that they were using, or that they use, is a GG25 tool steel material. Here you see a figure of the tooling. So these are in fact 2 door outers that you see. This is a surface scan of the tool surface, and the sheet material used was a CR180 bake hardening with an electro-galvanized coating. You see here a 3D surface texture of this sheet material. So at Daimler, they did different tests at different velocities, different lubrication amounts. So this is in tryout production. I have selected here the 3 most interesting ones. So first of all, if they use a punch velocity of 49 millimeter per second with a lubrication amount of 2.0, then they didn't find any cracks in the product. So the product was okay. But when they decreased the punch velocity to, for example, 50 millimeter per second, using the same amount of lubrication, then they found splits in the product. And also if they keep the velocity at 49 millimeter per second, but if they decrease the lubrication amount from 2 to 0.5, then they also observe cracks in tryout production. So at Daimler, they did different measurements. They did strain measurements, thickness measurements. They did geometry measurements to compare the geometry, spring back and draw in. And we have used this information in this project to validate the Triboform friction model. So if we look at the tryout production, we see the part in this figure. We also see the areas where strain measurements have been performed. If you look at the 2 corners, so at the left bottom side and the right bottom side, then these are the corners that if cracks occur, then you would expect that cracks occur in these regions, so in this corner. From this measurement, an FLD has been made. So we see here the forming limit diagram. The blue dots represents the strain measurements. So these are the experimental measured strains. This was also simulated using Autoform and a Coulomb friction coefficient of 0.15, which resulted in a strain distribution which is depicted by the red dots. So based on the outcome of the finite element simulation, you would have said, okay, this product is okay, it's okay for production. However, if you look at the experimental results, so if you look at the blue dots, then you see that a certain amount is exceeding the forming limit curve. So from this plot, you would say, okay, this product is critical, as some points are exceeding the forming limit curve. If we do this with Triboform, then we find the green forming limit curve, or the green forming limit diagram, where you see that the outcome is more critical compared to the Coulomb 0.15 case. So the results are now exceeding the forming limit curve. And if we now decrease the velocity, so if we go from 49 millimeter per second to 15 millimeter per second, then first of all, the results will become more critical. So in fact, cracks will be found in the part at this location and at this location. Also, if we look at the blue experimental strain measurements, it exceeds the forming limit curve. Coulomb, of course, remains the same because we're still using a Coulomb value of 0.15. But if we look at the Triboform results, then we will find a more critical behavior. So this comes because there is a velocity dependency in this EG material, which was used by Daimler. And if you decrease your velocity, this will have an influence on your tribology system. And in this case, you will have a higher friction coefficient. Well, if you have a higher friction coefficient, then also your part will become more critical. And this is what you see in these figures. So the next case was to reduce the lubrication amount from 2.0 to 0.5. Again, if we go to the tryout production, then they find cracks in the product at the same location, so at the corners of the part. Coulomb again remains the same, the Coulomb value of 0.15. And also, if you look at Triboform, the more critical results are found, and also in defined element simulation, you will now find cracks in the product. So this really gives a very nice overview of the TriboForm software and what you can do with the TriboForm software. So if we look at the results, so we see the results from tryout production. For the first case, it was critical but no cracks, so okay. And for the other two cases, we find cracks in the product. If you simulate it with Coulomb 0.15, then in all cases you have a green light to go to production because your FLD will remain below the forming limit curve. But if you do it with Triboform, then for the first part it's critical but it's okay, so no cracks. And also for the other two cases, you will find cracks in the product because the tribology system is changed. So the next application case is on the door inner of the Volvo XC90. Volvo had problems in production, so the production of the door inner now runs on 7 strokes per minute, and Volvo indicated that they wanted to increase the stroke rate to 14 parts per minute. However, if they increase the stroke rate, then they know that they will have wrinkles in the part. And on the other hand, if they do produce the part at 7 strokes per minute, then at a certain moment they have to reduce the cushioning force or the cushioning pressure because otherwise they will find cracks in production. Well, and their question was, could we predict beforehand which sheet material, which lubricant we should have used in production to overcome these issues and to increase the stroke rate to the desired stroke rate of 14. So the material they have used or they are using is a DX56D with a hot dip galvanized coating. The problems that they observe in production are depicted in these figures. So if they increase the velocity, so if they increase the stroke rate above the 7 strokes per minute, then we'll find wrinkles in this area and in this area, which is also shown in this figure. And if they remain at 7 strokes per minute, then at a certain moment, so after 200 or 300 parts, they will observe cracks, or they will have cracks in the part at this location, which is depicted by the split as given in this figure. So at Volvo, they did a full-scale production run of 2,000 parts, and during this production run, they did different measurements for different parts during this production run. They measured strains, they measured thicknesses, splits, they measured the geometry to compare the spring back and draw in. And this information has been used in this project to make a validation step of the TriboForm software. So if you look at start of production, they took out the part. Beforehand, they have applied a grid to the sheet material to do the strain measurements afterwards. Here you see a figure of the strain measurements, and you also see the corresponding FLD represented by the blue dots. And here you see that, well, a part is critical, so it's exceeding the forming limit curve. If they do that, or if they simulate it with Coulomb, then you will see that the part is critical. So there's a major part exceeding the forming limit curve. So from this simulation, you would say, okay, this product is critical. It should be noted, however, that it is not the original CAD data that is used for these simulations, but that the real 3D scans are used from the tooling as they are now used in production. So they did a full 3D scan of the tooling, so the punch, the die, and the blank holder, and these parts have been used in the outform simulation. And then using Coulomb, you would predict that you will have fracture in the product. If we do it with Triboform, then we will find the green dots. So you see that the form and limit diagram is more or less spot on the form and limit diagram of the experimental results, giving a very nice correspondence between the experiments and the predictions which are made by AutoForm plus the TriboForm software. So if you look at an animation of how the friction coefficient looks like for the door inner of the Volvo XC90, then we see that we have lower friction coefficients in the draw bead region. So I will play it again. So you see that at the draw beads and die radii, we will have lower friction coefficients because of higher pressures, higher strains. And we see that in the blank holder region, we will have higher friction coefficients because of the lower pressure and lower strain that is found in that region. And if you look at a zoom in, then here you see more clearly what I just mentioned, that if you are in a die radii, or if you have a draw bead radii, that you will find low friction coefficients. The blue color corresponds to a value of 0.11, 0.12, wherein underneath the blank holder region, you will find higher friction coefficients, around 0.15. And it should be noted that the red area is the area which is not in contact with either the die or the punch. So no friction coefficients are calculated over there. So the colored regions are the regions which are in contact. And in contacting regions, a friction coefficient is calculated by Triboform. And this friction coefficient is provided back to AutoForm to be used in defined element simulation, which is done for each node in contact for each increment of the defined element simulation. So if we have a closer look to the strain distribution, so we took out two cross sections over here and over here. You see here in black the major strain from the measurement. In purple you see the major strain from the defined element simulation using Coulomb, and the red curve is the major strain from the defined element simulation using Triboform. And then you also see that at a more local scale, so really at a cross section at this part, you will have a very nice prediction of the strain distribution using AutoForm in conjunction with the Triboform software. And the same holds if you look at this area. So we took out the cross section over here, and there we find the same conclusions, that you have a very nice correspondence between the experimental results and the Triboform results. So the geometry has been measured of this part. So we could also make a comparison in the draw-in. Blue is the production, so the part that was taken from the production. Red is AutoForm, and green is AutoForm plus Triboform. So red is AutoForm plus Coulomb. And then you see that if we zoom in at different parts, so if we, for example, zoom in this region, then you see that, in fact, the Coulomb will give a under-prediction of the draw-in, and the Triboform simulation is more or less spot on the experimental results. So this really has improved the prediction capability of the defined element simulation in terms of the draw-in and of the strain distribution, as we've seen earlier. The same conclusions can be drawn from the other figures. So if we zoom in this part of the part, then you will also see that we have with Triboform a more accurate prediction of the draw-in, and the same holds for this location. So this was in fact the start of the production run. This project is ongoing with Volvo. So what you see here in this graph is the cushioning force as function of the number of parts. And there you see that at a certain moment, so after 300 or 400 parts, they had to reduce the cushioning pressure to avoid fractures in the product. And after 600 parts, they had to reduce the cushioning force again. At the same time, they did temperature measurements to store or to lock the temperature during this production run of 2,000 parts. So, as I mentioned, this project is ongoing, but the TriboForm software gives you, the user, the possibility to investigate the influence of, for example, cushioning force or temperature increase on the tribology and on part quality. So using the TriboForm software, you can it gives you the possibility to look at temperature variations, but for example also to look at the influence of your sheet coating or the influence of your tooling coating on product stability. At Volvo, they also did a production run using DX56D plus a zinc magnesium coating. And using this zinc magnesium coating, they have increased the stroke rate to 12 without any problems. And also they didn't have to adapt the cushioning pressure during the production run. Well, and using the TriboForm software, this gives Volvo, this gives our users the possibility to simulate this effect and whether you can increase your stroke rate or that you should change your coating, for example, to get to the stroke rate that you want in production. So from this, we can also make quite an easy TCO scan. So if they have used the zinc magnesium coating with the assumption that they produce 100,000 parts a year, that they could have saved 120,000 euros on this part if they would have directly shifted to the zinc magnesium coating. Okay. So if we look at calculation times, because we often got the question, well, you add functionality to a finite element simulation, you add functionality to AutoForm. What does it do with the simulation time? Well, we have four different cases in this table. So we have quite a simple cup. We have the front fender, we have a door inner, and we have a door outer. Well, and if you look at the increase or decrease in simulation time, then you see that we either find a decrease in simulation time or we find a small increase in simulation time. Well, of course, we are adding more physical behavior to the finite element simulation because we're accurately account for the tribological effects. And this also have an effect on the simulation time, as you see, and which can also be have a positive influence on the simulation time. So next is the closure. So first of all, I would like to discuss the benefits. So using the TriboForm software, well, as we have presented, it's a high impact software solution for friction and lubrication modeling. It gives you access to a database of friction models. So the only thing you see as a user is the TriboForm Analyzer. You can select your tribology system, so your sheet metal lubricant combination, and export this friction model to your finite element simulation, which gives you an efficient approach for handling an increasing number of tribology systems. So it gives you an approach to quite easily change the sheet material, the lubricant, or the tooling material, and see what the effects are on part quality. Implementation in finite element software. Using these two application cases, we have shown that we provide an improved simulation accuracy of critical quality factors. It gives you a reduction of simulation time or a minimal effect on simulation time. It provides enriched simulation possibilities, so it really allows you to account for the real Tribology system in your find element simulation. And it also gives you a proven return of investment for customers, as we have seen from the Volvo demonstration case. So the TriboForm software is used by, let's say, the leading automotive OEM companies and suppliers, and we are expanding. You can, using TriboForm software, execute friction variation studies. So as I mentioned, you can change your sheet material, your tooling material, or your lubricant. But it also gives you the possibility to variate in sheet roughness, tooling roughness, and lubrication amount. And we're also focusing on new developments in the field of hot forming and galling. And regarding galling, I have one additional slide. So that is on the simulation of galling and tool pollution in sheet metal forming processes. So galling is indicated by most of our customers as the #1 problem in production, so that the zinc material of your sheet or the aluminum adheres or sticks to your tooling, resulting in scratches of your product. So we are currently developing a model that accounts for, let's say, the material pickup from your sheet to the tooling. And the newest developments you see here in this sheet. So we have an input screen where we can read in find element results. And here we can select that we want to calculate galling, for example, or tool pollution. And then we will see the amount of material after a certain number of presses that sticks to the tooling material. So here you see an animation as function of the part number. So here we look over parts from 0 to 900. And here you see the amount of material of your sheet material that sticks to your tooling surfaces. And at a certain moment, this material which is built up on your tooling side will result in scratches in your final part. So the cases that we have discussed today can also be found on our website, www.triboform.com. Here you will find a summary of the Volvo and the Mercedes, the Daimler case, but also a case of Skoda and Tata Steel. And well, if you are interested in using the TriboForm software, then please contact me directly or go to our website and start your free trial. Well, and thank you for your attention. So this was the presentation. Thank you for the attention.
Okay. Thank you very much, Jan. That was very, very informative. And those of you who joined our meeting today may have noticed that we had posted some information on various social networks regarding the invitation to this event, and I had received some questions on LinkedIn and Facebook and Twitter where people were feeding back to me some questions, and I had them ready to ask you, but actually you've already answered them in your presentation.
Okay. That was a good presentation, I guess.
It was an excellent presentation. You answered many of the questions before we had a chance to ask them, because
Okay.
there were a couple things that I caught during your presentation. I was actively typing in the chat window as you were leading the discussion today. Hopefully some people find some interesting value out of them. One of the things that you mentioned toward the end is the idea that sometimes a simulation inside of AutoForm converged faster and sometimes it converged slower. And
yeah.
that of course is because inside of AutoForm, as you decrease forming severity by having this better modeling of the tribological system, then if forming severity goes down, then computations run faster. in AutoForm. And when the forming severity is worse because of this better modeling of the tribology, then the simulation takes longer because we start to see increased discretization of the elements. We see
Yeah.
more
Yeah.
adaptation, and then the time steps take longer. So it really has no significant effect on computation speed. It's not like it makes it run twice as long or half as long, but instead you see
No.
this minor percentages. So that's quite important
Yeah.
for my customers as well as your customers to realize that it's some upfront engineering work to create better input values, but each iteration of the simulation now happens for the same tribology system would be more or less the same computation time.
Yeah. That's correct. Yeah.
Okay. Well, thank you very much. That was very enlightening. I'm going to do the always risky thing, which is I'm going to unmute everybody's microphones to give them an opportunity to let them ask any questions that I didn't envision. So just one moment
Yeah.
as I unmute all the microphones. And if any of you who are joining us online today have a question, please go ahead and speak up at this time. Hello, everyone. Your microphones are now open. And if you have a question, you could go ahead and verbally say your question out loud and we could answer it. Or if you're more comfortable, you could type it into the chat window and we could have an answer from Dr. Hole. See, this is what happens when you're so thorough.
Apparently. Everything was clear, I guess.
Everything was just so clear. Everyone had no new questions, but
everything's answered, or we're still just recovering from just seeing the new developments in the simulations.
I myself have to say that I was very pleased to see that you had announced the release of the software a few months ago when we invited you initially to join, because that was always the biggest lingering question that would come from customers who I have trained how to use AutoForm is, what do I put in for friction? And
Yep.
we would tell them that 0.05 is sometimes a conservative number, but we also see that sometimes 0.15 is not conservative enough.
No, that's correct.
And I was also very pleased to see in the case of that door outer, the somewhat counterintuitive conclusion that for outer skin panels with relatively shallow draws and large surface areas of stretching over large contact areas, that lower press speeds sometimes do result in higher coefficients of friction. And
Yep.
I know many people who work in deep draw who make maybe those door inners for a living, and they say, well, inching the press down was better. And I myself would try to tell them about some of these parts I've worked on in outer sheet metal and tell them, no, we made much better part quality when we ran the press fast, because for some reason in this performance I knew it would run better, but I had no physical proof, and I couldn't capture that in simulation without the benefit of a velocity and pressure dependent friction model.
Yeah. Well, the TriboForm software gives you the possibility to include this effect and to see what the influence is of velocity on part quality.
Well, very good. Okay. Brian thought maybe that echo we were hearing was because you somehow might have phone and webcam audio. I don't know. At this point,
as well.
Yes. There's a question here. Let's see. Ruzgar Peker asked the question: how did you create your library?
What we do is we do a specific experiments. So if we analyze a new tribology system, then we speak about a certain lubricant, a certain sheet material, and a certain tooling material. We in-house have the TriboForm solver, and the TriboForm solver we use to generate this friction model. And the TriboForm solver is based on physically based models. So we really account for the physics of tribology to calculate a four-dimensional friction model. And as an input for this, we require the three-dimensional surface texture. So that's the same texture as shown in the presentation today. So we require three-dimensional surface texture. We require information about the material, so the yield strength. We require information about the lubricant, so the viscosity, for example. And if you have all information in place, then we can create a TriboForm friction model, and we store all this information in this library. And this library is then the library that we provide to our customers to load a tribology system and to evaluate and analyze their tribology system and to use it in finite element software.
Okay, so when you describe to people that you have a library, the library is really the individual components of some standard sheet options, some standard lube options, and some standard tool surface options. And of course, you mentioned already too that if there was an option that did not exist in your library, that people have the opportunity to describe that by inputting peaks per inch and surface roughness descriptions. And is there did I understand there's a way that people can import in a surface topography?
Not in the current version.
Okay.
So as you just mentioned, 2 months ago we have released the first release of our software. In this first release, you can only, let's say, see the surface textures that are stored in a library. But in one of our next releases, it will also be possible to read in your own 3D surface textures and use this surface texture in the friction analysis.
Okay. And then the other question came from, again, Rusgar Peker, was did you use a lubrication evaluation method like the strip draw or the twist compression, or do you have certain assumptions that you're making?
We are not using, let's say, strip dot testers to get a friction coefficient, because that is what we calculate. We calculate friction coefficients. As an input for our models, we have, however, do have to do some experiments, and these experiments are based on deforming a surface by a specific load. So, for example, with 50 megapascals. This can be done on a strip dot tester. So you load a surface with a specified load, and then measure the surface deformation, and that is an input that we use to calibrate our model. So this is one of the experiments that we have to do to calibrate the TriboForm solver for a specific metal lubricant combination in advance to generate the TriboForm library.
Yeah. And one of the things I also suspect is one of the challenges when we think about empirical testing for coefficient of friction and lube performance and tooling, tool surface and lube performance is that the pressure and velocity regimes that are attainable in the strip draw are not necessarily the same pressure and velocity regimes that you might capture in a twist compression, and are certainly different than those you see from those shallow cup draws or LDH type environments. And that's always been the problem with experimental testing for friction coefficients, is that we were usually limited that strip draw you get good velocity correlation, but you never attain the pressure regimes that are necessary. And twist you get good pressure regimes, but you don't get velocity. Cups you get neither, right? When you do cup draw, it's like, well, it's not really fast and it's not really high pressure. And same for the LDH tests.
Correct. Yeah.
So
and using Triboform, we only require some experiments, which can be easily done on a normal strip draw or twist test experimental device. And then we use this information, we generate a friction model, and this friction model is easily applicable to larger or to higher pressures, to higher velocities, and higher temperatures. So it are some calibration tests that we have to do, but after that we can generate a four-dimensional friction model, which is independent of the limitation of your friction tester.
Hopefully that answers the question from Ruzgar.
Yep.
What other questions or comments does anybody have regarding the presentation and also the questions and answers that have been given after the presentation today?
Okay.
Okay, well, I think we're more or less on time, which is amazing. Again,
Okay.
thank you very much for joining us today, everyone at Triboform. It's a very impressive innovation that you had today. To be able to see it live was quite informative. Again, for everyone who is joining us, if you do think of further questions or things that you want to follow up, you certainly can contact. Dr. Hole has his email address there on the bottom. That's j.hol@triboform.com. You can also always send me an email. That's eric.kam@autoform.com. And I would be able to also communicate any questions that come to us to you. So thank you very much again.
Okay.
And at this time, I'm going to go ahead and stop the recording. And again, thank you very much for your time today, and look forward to working together with you in the future on other topics.
Okay. Well, thank you very much for the invitation and for the possibility to present our software at your forum. And hopefully, yes, we have a very nice, fruitful cooperation in the future.
Okay. Thank you very much. Goodbye,
Thank
everyone.
you. Bye-bye.
Thank you. And best of luck.